Good morning. Last session I have been talking about importance of secondary refining. I have just started taking up the topic. The whole idea is to refine whatever elements are present to whatever extent possible, control the inclusions and increase the cleanliness level. I have talked about what is the limitation of primary stage, why it is not possible to enhance cleanliness in this primary stage, because the slag here is very rich. Iron oxide in the slag is more than 20%. There is some amount of MnO, some amount of P2O5, which will create problem during the subsequent stages if this slag is not restricted. Even in the secondary refining stage, if this slag goes, there will be a problem. So, because the slag is rich in FeO, liquid still in primary stage, that means that has dissolved oxygen more than 500 ppm, which is very, very high, and this causes total oxygen to be more. That means it is dissolved, as well as if the dissolved oxygen is more, there will be more chances of formation of oxide inclusions, and so as a whole cleanliness is poor. And since dissolved oxygen is more, desulphurization is not effective at this stage. Recovery of alloying elements are poor because of this high dissolved oxygen. Alloying elements, they will be forming oxides, their yield is less, it is erratic, you do not know how much you will finally get. So, it is difficult to achieve close chemistry as well as cleanliness. Now, I have told that this primary stage these days is basically used as a fast and efficient process for melting and preliminary refining. That means basically to control carbon, silicon and phosphorus and getting a base chemistry on which you can fine tune during the subsequent secondary refining stages. Now, I have also covered what is the role, what is expected in the secondary refining stages. First, liquid steel is tapped from basic oxygen furnace or electric arc furnace in ladle. So, subsequent treatment in ladle, what are expected? We should get a narrow ranges of alloying elements, we should get a homogeneous composition as well as homogeneous temperature throughout the liquid steel, but we must get improved cleanliness. That is the principal requirement for secondary refining. So, what are the desirable functions? I have talked about. First is deoxidation, which is known as killing. This is the first requirement for any secondary refining process, and it is a primary requirement for getting a clean steel. Next is decarburization, or in one or two cases even carburization, that means control of carbon in the bath. Then desulphurization or sulfur addition in maybe one case only when you need more sulfur for good machinability. Otherwise, in most of the applications we require less sulfur. So, desulphurization is one important requirement. Then control of gaseous elements like nitrogen and hydrogen in liquid steel. This is done through degassing. I will come to this in details later on. Then maybe injection of Ca or Ca. Basically, injection of calcium helps in inclusion modification, making the inclusion liquid at steel making temperature, and it is easier to float them up and get absorbed in the slag, basic slag. And finally, control of liquid steel temperature. This is essential if you want to do a good casting. Now, I had talked about what are the common secondary refining processes. I have talked about ladle furnace, which is a very common process. Most of the steel producers today have ladle furnace. I will come to what ladle furnace can do, what are the capabilities. Then inert gas purging in ladle. This is very simple. At the bottom of the ladle, through the bottom of the ladle there is a gate through which you can pass inert gas, say argon. So, it is possible to make a good circulation in the bath becomes homogeneous. This helps in some reactions like deoxidation reaction, floating of deoxidants and related advantages are there. Then I have talked about the vacuum processes. It may be vacuum degassing, where degassing is possible, you create vacuum. We will discuss today how it helps in degassing. Then we can have VAD, that is vacuum arc degassing. That means on top of vacuum there is a facility of arcing. That means you can control the temperature, you can increase the temperature in the liquid bath, in the liquid still. So, even if there is a temperature decrease during the process, it is possible to get back to the desired temperature using arcing. Then we can have vacuum oxygen decarburizer, VOD. What does it do? There is vacuum as well as you are passing oxygen. So, that this helps in decarburization. That means oxygen will react with carbon, will generate carbon monoxide, which is a gas, and if you have a vacuum, this carbon monoxide removal becomes easier. So, it is an efficient process for decarburizing. So, VOD is basically vacuum oxygen decarburizer. Then I have talked about RH. Today I will discuss what are the specialties of RH, why it is beneficial, how it is different from other degassing and related issues. So, RH basically stands for Root-Stahl-Heraus process degasser. It is basically degassing. In this process you can bring down oxygen and nitrogen in steel. It was invented in Germany. So, it is known as Root-Stahl-Heraus degasser, RH degasser. Then there is a possibility of injection metallurgy. That means you are injecting either some powder or some wire of calcium. So, injection metallurgy is possible in the ladle. By that process you can get better control of the inclusions. I will come to that later on. Then I had discussed this how these capabilities are actually taken care of or taken benefit of in the different processes. I have told deoxidation, which is the primary requirement of a secondary refining process. It is possible in all the known secondary refining processes, whether it is VD, whether vacuum degassing or vacuum arc degassing, ladle furnace, vacuum oxygen decarburization, injection metallurgy, inert gas purging. In you name any secondary refining process, deoxidation is possible. Then desulphurization, it is possible in most of the secondary refining processes, whether it is VD, VAD, LF, VOD, injection metallurgy, inert gas purging, everywhere it is possible. Only thing is in inert gas purging it is relatively less, but if you can add some calcium oxide, that means you can create a basic slag, then you can get some amount of desulphurization in inert gas purging also. Then decarburization, I have told you it is possible only in VOD, when along with vacuum you have some oxygen ingress in the facility. So, oxygen reacting with carbon can give rise to decarburization. So, this is possible in VOD. Then heating, I have told you whenever there is an arcing facility you can do heating and you can increase the still temperature, liquid still temperature. So, this is possible in VAD because you have arcing. It is possible in ladle furnace because you have arcing. It is possible in VOD through addition of aluminum, because it is aluminum and oxygen will react and will give some chemical heating. So, it is possible to some extent in VOD. It is also possible in RH, which I will discuss today in details, where it is possible to increase the temperature through some heating. Then degassing, I have told you whenever there is a vacuum in any process, whenever we can increase the vacuum level, there is a possibility of degassing. That means removal of nitrogen, gaseous elements like nitrogen, hydrogen. So, vacuum degassing, it is possible in VD, VAD is possible in VOD because there is vacuum. It is also possible in RH. I will discuss this today. Then I have talked about inclusion modification. That means you can change the inclusion by putting some calcium. So, it is possible in VAD, it is possible in LF, it is possible in injection metallurgy, definitely it is possible, it is to a minor extent possible in IGP. Now, I have also discussed in the last session that how deoxidation takes place, which is the principal requirement of any secondary refining process. So, it is a reaction between the deoxidant M with oxygen, which is present as element in liquid steel. So, as a residual element. So, this reacts and the formation is MXOI. So, M can be any deoxidizer, manganese, silicon, aluminum, calcium, anything. So, depending on the element or the deoxidation product can be manganese oxide, can be silicon oxide, can be aluminum oxide, can be CO, or a combination of this if you have 2 or 3 deoxidizers which can be used for deoxidation, which is known as complex deoxidation if you use more than one deoxidizer. So, from this reaction we know the equilibrium constant is basically related to the activity of the deoxidant divided by the Henryan activity of the metal, which is causing deoxidation. It is multiplied by the Henryan activity of oxygen, soluble oxygen in liquid steel. Now, if we assume the deoxidation product as pure oxide, we can take the activity of the deoxidant as 1, and so assuming Henry's law for dilute solution, where activity can be taken at weight percent because it is much low, very very low, is a dilute solution. So, Henry's law is valid. So, the wet fraction of the element deoxidant in liquid steel to the power x into the wet fraction of oxygen in the liquid steel to the power y, it is constant. It is known as deoxidation constant. So, I have also discussed that from this value of the constant, because wet percent of the deoxidant into the wet fraction of the oxygen is constant at a particular temperature. So, from the value of the constants, like at 1600 centigrade, which is is a common liquid steel temperature, if at this temperature if you evaluate what is K from the thermodynamic values. So, we can get that manganese, for manganese this K value is 0.2 to 0.3, silicon it is about 2 into 10 to the power minus 5, aluminum it is 3 into 10 to the power minus 14, it is very low, calcium around 10 to the power minus 12, very low. Now, the lower this value, what is the advantage? That means for a particular amount of M, the multiplication is lower, means the oxygen also will be low. That means when you are using the same amount of deoxidant, if the value of K is low, that means for aluminum and calcium, the soluble level of oxygen, dissolved oxygen also will come down for when you are using aluminum and calcium. So, using the same amount of deoxidizer, soluble oxygen will be very low for calcium and aluminum, moderate for silicon, and relatively high for manganese. So, therefore, of the common available elements, easily available elements, aluminum has been extensively used as a strong deoxidizer. We have taken up these issues in the last session just to make you understand that from the basic theoretical values we can know which one is a good oxidizer, which one is a relatively poor oxidizer, to what extent deoxidation is possible. Now, I have also discussed what are the stages of deoxidation. That means, when we are adding the deoxidant, what are the steps, how does it react? First we have to add, and then this gas gets into the solution, that means dissolution of the deoxidizer in liquid steel. So, when we are adding aluminum in liquid steel, first it has to get dissolved, that means the dissolution of aluminum in liquid steel is the next step. Then there will be a reaction between this dissolved oxygen and dissolved aluminum in liquid steel. So, first we are adding aluminum, it is getting dissolved in liquid steel, then this dissolved oxygen and dissolved aluminum in liquid steel, they are reacting, and nucleation of alumina particles, that means the deoxidation product alumina is getting nucleated, and there is some initial growth, and all these 3 steps they take place very fast. So, we get nucleation of alumina and some initial growth of alumina particles. So, at this stage of deoxidation, what is the situation? We get dissolved oxygen and dissolved aluminum, which are very low, because dissolved aluminum has reacted with dissolved oxygen, and cis aluminum is a very good deoxidant. At a very low amount of aluminum, dissolved aluminum, we get very low amount of dissolved oxygen. But what is happening? What is the deoxidation product? This is alumina. So, these alumina particles which are nucleating, and there is some initial growth initially at the start, these alumina particles are still in liquid steel. So, alumina is relatively high. We have very low dissolved oxygen, very low aluminum, but good amount of very low aluminium as element, but good amount of alumina, the deoxidation product. So, this alumina from liquid steel has to be removed, then only we get good cleanliness, and thereby the total oxygen, which is a combination of dissolved oxygen and oxygen present as alumina. So, if we can remove this alumina from the steel, we get good cleanliness, low value of total oxygen. Now, how is it possible? This growth of the alumina particles, they happen by agglomeration. That means, these particles, they combine with each other, agglomerate with each other, they will float up, and subsequently they will be absorbed by the basic slag. But the whole this process, this was very fast, formation of alumina, but this growth of the alumina particles, they are floating up and getting absorbed by the top liquid slag. It takes time. So, we have to give that sufficient time, that adequate time for the inclusions to float up and get absorbed. Now, I have talked about you that how the flotation and consumption of aluminum oxide takes place. I have talked about Oswald ripening. This helps these alumina particles to coagulate and form larger particles. Why it happens? Why these smaller particles grow, the smaller particles combine and form larger particles. This is basically from the surface point of view, surface tension, surface energy point of view, because smaller particles have relatively larger surface area, surface to volume ratio is more. So, that means if they combine, if the smaller particles combine, the surface to volume ratio will come down. So, the surface energy also will come down. From this point of view, we call it Oswald ripening. Small particles, they will combine and large particles will form. Now, we know that from Stokes law, these particles, how they will, what will be their velocity when they float up? It is related to, it is proportional to the square of the size of the particles, and it is directly related to the density difference between the liquid and the solid particles. We know these solid particles, that means alumina or SiO2, whatever are the deoxidation products, they have relatively less density compared to liquid steel. That is the reason why they will float. That is the reason why the velocity will be dictated. That is the reason why that, or rather another reason for the velocity to go up is the size. The more is the size, that means larger is the size of the particles, more is the velocity. That means larger particles will try to float up because of this Stokes law, and then they will be consumed by the basic slag. Basic slag means which has very high amount of calcium oxide, which has good basicity. So, they will consume these alumina or SiO2 particles, which are basically the deoxidation products. So, duration of argon purging, this is very important. Adequate duration of argon purging, say about 15-20 minutes is necessary to allow these particles to float up. These larger particles are harmful. So, fortunately, if you give some good time for this adequate time through argon purging in the ladle. So, this harmful large NMIs, they will float up and get absorbed by the basic slag. So, I have told you how these alumina oxides are forming. That means you are adding aluminum as deoxidant. It is causing the dissolved oxygen to come down. So, we have dissolved oxygen and dissolved aluminum in steel, as well as alumina as particles. These alumina particles will try to float up, they will try to coagulate and try to become bigger, and then the bigger particles will float up. This process is enhanced by use of argon purging, because it helps the larger particles to form faster and larger particles to go up, float up and get absorbed by the slag which is basic in nature. Then I have also talked about some important issues of deoxidation. What are the issues? The carryover slag from primary furnace, I have told, towards the end of tapping there is a possibility because of this funnel formation. So, this has to be low, because this carryover slag, that means the slag from the primary steel, I have told you, it is very rich in iron oxide, more than 20%, it may be 25%, it may be slightly more. Then there is about 5% MnO, then there is about maybe 3% phosphorus oxide, which has removed phosphorus from liquid steel to the slag. So, all these oxides, FeO, MnO, P2O5, they can react with the dissolved aluminum in liquid steel. Where from dissolved aluminum is coming? Because by the process of deoxidation, when you are adding aluminum, some amount of aluminum will be retained in liquid steel as dissolved aluminum, and the other portion of aluminum will react with dissolved oxygen and form alumina, and this alumina we are trying to float up and get rid of it in the process of for the removal. But if you have some amount of carryover of slag from the primary furnace, then what is happening? This iron oxide, which is present in the carryover of primary furnace slag, this will react with the dissolved aluminum in liquid steel, it will again generate some alumina. Then phosphorus oxide, by removing phosphorus, by controlling phosphorus, lot of amount of phosphorus has got transferred from the liquid steel to the slag. Now, if this slag from the primary steel comes to the ladle at the end of the tapping, then whatever phosphorus oxide is there in the slag, it again might react with aluminum and there will be phosphorus reversal. So, the possibility of reoxidation and phosphorus reversal in liquid steel will be there if we cannot control the carryover of slag from the primary furnace. So, this is an essential requirement. Now, what happens if the dissolved aluminum, because of these reactions with FeO and P2O5, this amount of dissolved oxygen will come down by reaction, dissolved aluminum whatever was present due to reoxidation, this will come down, and in the process what is going to happen? Because the weight percent of this dissolved aluminum and weight percent of the dissolved oxygen is constant, as I have told you earlier. So, if the dissolved aluminum comes down, dissolved oxygen in liquid steel will increase. So, what is going to happen? This is going to affect the cleanliness of the steel. So, reoxidation will take place, phosphorus reversal will take place, that means phosphorus also will increase in steel, because some soluble aluminum is coming down because of these reactions, dissolved or soluble oxygen in liquid steel will increase. So, these are creating a cleanliness problem. So, effective slag stopper, I have told you, is very, very important. We must stop the slag from the primary steel making process, that means BOF or EF, to come to get carried over to the ladle at the time of tapping. This is very important. Then I have told you the basic slag and basic refractory, these are essential. Because why? If you do not have basic refractory means refractory which is rich in CaO. If you have some amount of SiO2 in the refractory lining, then this SiO2 will again react with aluminum in liquid steel and generate SiO2, reoxidation will take place, dissolved aluminum will come down, dissolved oxygen will go up. So, this is again a problem. So, basic slag is required to take care of the alumina, to take care of the SiO2 deoxidation products. So, basic slag and basic refractory, these are also essential requirements. And then I have told you that this adequate time, say about 15, 20, 25 minutes is necessary for argon purging to allow the alumina inclusions to float up and get absorbed. Now, today let me talk about another important requirement called desulphurization. I have told you the deoxidation is the first requirement for secondary refining. You have to first deoxidize the steel. That means the oxygen, soluble oxygen level must be brought down, then only the subsequent reactions are really effective. I will come to that now, why it is required. Initially there has to be a deoxidation, then only desulphurization reaction is effective. Now, what is desulphurization? Let me first talk about that. Desulphurization basically means whatever sulfur is present in liquid steel after primary steel making. As I have told you, since there is lot of iron oxide in the primary steel making slag, so the oxygen, dissolved oxygen level is also very high, and if the dissolved oxygen is high, desulphurization is not very effective, which I have already discussed earlier, and today I will come to it also in a more elaborate fashion. Now, what is the desulphurization reaction? The sulfur, whatever is present in liquid steel, it will react with calcium oxide which is present in the slag. So, what is the essential requirement? Requirement is there has to be good amount of calcium oxide in the secondary refining slag. That means we must add calcium oxide in ladle, so that the slag contains good amount of calcium oxide. What is meant by good amount? It has to be, say, about 50%. That means the basicity of the slag, CO by SiO2 should be very high, maybe more than 3. So, the calcium oxide should be at least about 50%, basicity should be more than 3. So, this is one important requirement. Now, what is the reaction? Slag metal reaction. First bracket I have told you indicates that it is a presence in slag. So, CaO whatever is present in slag will react with sulfur which is present in liquid steel. You see, it is third, we have given third bracket for the sulfur. That means calcium oxide in slag is reacting with sulfur which is present in liquid slag, not in liquid slag, liquid steel, third bracket is liquid steel. So, calcium oxide present in slag, sulfur is present in liquid steel. So, these two are reacting for the formation of calcium sulfide, which is going to the slag, and oxygen is getting generated which is present in liquid steel, third bracket, that means liquid steel. So, the reaction is between sulfur in liquid steel with calcium oxide which is present in the slag and generating calcium sulfide which goes to the slag, and oxygen which goes to the liquid steel. Now, the equilibrium constant for this reaction, what does it indicate? That the activity of the calcium sulfide in slag into activity of H is basically the Henryan activity of oxygen in liquid steel divided by activity of calcium oxide in the slag into activity, Henryan activity of sulfur in slag, in liquid steel, sorry. So, the activity of calcium sulfide, the sulfur whatever was present in liquid steel is going to slag as calcium sulfide, and the oxygen whatever was present in slag as calcium oxide is trying to, part of it is trying to come in liquid steel in the form of elemental oxygen. So, that means this reaction is basically a slag metal reaction. So, the equilibrium constant is basically K dash is basically activity of calcium sulfide, that means the sulfur in slag into the activity of oxygen, Henryan activity of oxygen in liquid steel divided by activity of calcium oxide in slag into activity of sulfur in liquid steel. So, what does it indicate? How the reaction will be faster? It can be faster when we have very good amount of calcium oxide in slag, we have very low amount of dissolved oxygen in liquid steel, because you just see, look at the equilibrium constant, activity of calcium sulfide into activity of oxygen divided by activity of CaO and activity of sulfur. Now, assuming that calcium sulfide and calcium oxide in slag are related to weight percent of sulfur. So, calcium sulfide I am trying to convert it to the weight percent of sulfur, and calcium oxide, if you assume whatever weight percent is present in slag. So, calcium sulfide and calcium oxide, they are present in slag, and if you assume their activity to be related to the weight percent of sulfur in slag and the weight percent of CaO, that means calcium sulfide I am trying to represent with weight percent of sulfur in slag, and this Henryan activity of sulfur and oxygen in liquid steel related to their weight percent in liquid slag, because they are very small, weight percent of sulfur, weight percent of oxygen in liquid steel is very small. So, we can represent them by weight percent Henryan activity, that means Henry's law is effective here for dilute solution. So, what is the sulfide capacity is a new term. Sulfide capacity is the weight fraction of sulfur in slag, first bracket, divided by weight fraction of sulfur in liquid steel, third bracket. So, what is happening? The sulfur from liquid steel is going to sulfur in slag as calcium sulfide. That means the weight fraction of sulfur in slag divided by the weight fraction of sulfur in liquid steel. So, this ratio, more is the ratio, more is the desulphurization. Is it clear? Ws is the weight of sulfur present as calcium sulfide in slag, because the reaction is calcium oxide in slag reacting with sulfur in liquid steel to generate calcium sulfide in slag and oxygen in liquid steel. So, whatever sulfur was present in liquid steel, the idea is to transfer as much as possible from the liquid steel to slag as calcium sulfide. So, the weight of sulfur in calcium sulfide present in slag divided by the weight of sulfur in the liquid steel. So, that ratio is known as the sulfide capacity. Higher this ratio, that means more is the amount of sulfur in slag as calcium sulfide, more is the sulfide capacity, better is the desulphurization. Now, this is equal to what? This is equal to 1 divided by K dash, that means another constant into weight of CaO in slag divided by weight of oxygen in liquid steel. So, just look at this ratio. So, the sulfide capacity Ls, which is an indication of how good is the desulphurization, is basically proportional to weight of CaO, that means weight of calcium oxide in the slag divided by the weight of oxygen in liquid steel. That means, this is directly proportional to the CaO percentage in slag, but inversely proportional to oxygen present in liquid steel. So, lower the liquid steel oxygen, better will be the sulfide capacity, better will be the desulphurization. Now, is it clear why every time I have been talking about the deoxidation has to be first done? If deoxidation is done, oxygen level is in steel comes down. This helps not only in creating low amount of total oxygen, but also helps subsequently in desulphurization. So, high CaO in secondary refining is essential. Also, low oxygen in liquid steel, that is good deoxidation, is also essential. So, there are two requirements for having good desulphurization. First is good amount of CaO, more than 50%. The basicity has to be, basicity means CaO by SiO2 ratio in slag has to be more than 3.5 is better. And another important requirement is the oxygen liquid steel has to be low. That means good deoxidation prior to desulfurization is essential. So, for all secondary refining, again I am repeating, first activity is deoxidation. Once we achieve good deoxidation, that means the solubility of oxygen in liquid steel is brought down to say less than 5 ppm, then desulfurization will be very effective. I think it is very clear to you now why first deoxidation is necessary and then desulfurization is good desulfurization is possible, and I am giving you a concept of sulfite capacity of the slag. That means the slag must have very good amount of CaO, then only it can hold on to the sulfur in the slag. That means the sulfur wet percent of sulfur in the slag in the form of calcium sulfide will be more when you have mole calcium oxide. So, this sulfite capacity of the slag is very important. That means we must have adequate CaO in the steel, which will generate adequate calcium sulfide in the steel, then only we have wet percent of sulfur in the steel is more compared to the wet percent of sulfur in steel. This ratio is important. So, the amount of slag also comes to the picture, because if the amount of slag is less, this ratio, there is a restriction on the ratio, it cannot go high, and desulfurization is not very effective. So, good amount of slag having high amount of CaO and basicity and very low oxygen in liquid steel, these are the requirements for effective and very good desulfurization.